All right, let's do it to it. All right, so today we are going to begin our next topic on infinite horizon dynamic optimization, otherwise known as, or one way of solving these types of problems is with something called dynamic programming. So what I want to do for the next few classes is basically just introduce this infinite horizon optimization problem, kind of a generic form of that problem in what's called discrete time. You all know what that is. So it's not a continuous time model, but a discrete time model under certainty, meaning that there is no source of random variation in these models yet, okay? So the solutions to these models are sometimes referred to as perfect foresight solutions, all right? The planner can solve a dynamic optimization problem and know for certain what's going to happen over time. There are no shocks. Later on in the semester, we'll introduce uncertainty into the dynamic optimization apparatus. We're going to first introduce this basic problem and then try to present several results necessary for the application of dynamic programming, okay? Now, I might use the term stationary dynamic programming. I may drop the stationary part, but it is just assumed that we're talking about stationary problems here. All right, so for example, in the solo model, we did this transformation where the variables were written in intensive form so that they have a stationary solution, that there's a steady state in the long run. We're going to assume that the underlying model here is one that is stationary as well. The variables don't blow up in equilibrium, okay? Once the whole idea here is for you guys to get comfortable enough with the basic theorems that illustrate how to apply these dynamic programming principles and properties so that we can use these tools in order to analyze the optimal growth model. That is this infinite horizon representative agent growth model that I'll actually introduce in class today to show you how it kind of fits into this framework, but we won't analyze it in depth until next week, okay? That's the goal here, is to really familiarize yourselves with this mathematical toolkit so that you can analyze these types of growth problems correctly, okay? All right, so with that said, I'm gonna start by illustrating the basic, what I call in the notes, the canonical infinite horizon program, where you can think of this as just the generic infinite horizon program. It looks like the following. A planner is going to maximize over sequences of X and Y's that I'll define here in a minute, the infinite sum of discounted values of some payoff function U tilde, which depends on xt and yt, subject to some constraints. One of them is that yt is an element of some set called g tilde that I'm going to define in a minute. All this stuff may seem very esoteric, but it'll be clear in just a moment. Xt plus 1 is equal to some function f tilde of xt and yt. These hold for all t. And the initial value of x is going to be given in the problem. Okay? That's what the generic discrete time infinite horizon maximization problem looks like. Now, let me define some of these concepts. One of these, hopefully you already know, that's beta. Beta is the discount factor between 0 and 1, right? So near-term payoffs are more valuable to the planner than distant payoffs, right? You discount at rate, well, I guess you discount with a discount factor of beta. Okay, what is xt? Xt is a vector, okay? And it's going to belong to some space that I'm going to call capital X, which is a subset of the Euclidean space of dimension k sub x. Okay. Xt is what's called the state vector in these problems. In other words, at the beginning of date t, when a planner is trying to maximize this object, she actually knows the value of the state, right? That is what is known at the beginning of date t, all right? Here we're just saying that x belongs to some compact subset of Euclidean space, k of dimension kx, where kx is just some integer, okay? In the optimal growth model, this is going to be dimension 1, okay? But it can conceivably look at multidimensional objects here. So kx is an integer, and we're dealing with Euclidean space. What is yt? Yt is an element of some space capital Y, which is a subset of, let's say, RKY. Again, this is, let's say, KY dimensional Euclidean space, where KY is just some other integer. Y is what's called the control vector. This is the endogenous element that the planner is choosing over time in order to maximize the value of this objective, infinite horizon objective. So xt is the control vector, right? And yt is the xt is the state vector, and yt is the control vector, right? Yt is what's chosen by the planner. Xt is what's taken as given by the planner at the beginning of period t. Now, what is U tilde? This, as you might imagine, is an instantaneous payoff function that maps elements of x product y into the real line. All right, so the payoff function gives you just a scalar. It takes x and y, which are potentially vectors, and gives you a single scalar number which ranks those bundles of states and controls. Okay? It's the instantaneous payoff function. You can think of it as the utility function in an economic application. Okay? Now, what is this object then? This is the infinite sum of current and future discounted instantaneous payoffs. This is the lifetime objective function that the planner is trying to actually maximize. Okay? So the planner is not maximizing instantaneous utility so much as she's maximizing discounted infinite horizon utility or payoffs. That's the overall objective. This is the instantaneous payoff function. Okay. Here is another part that is somewhat complicated and new to most students, and that is this term G tilde. Now let me explain what that is. G tilde is what's called a set valued mapping or a correspondence, okay? It takes elements in big X and maps them into the space of Y's, okay? Now to think about what this is properly, this is not a function, okay? This doesn't take an element of X and give you a specific element of Y. What G tilde is a set value mapping that shows the following. It essentially gives you all of the feasible values that Y can take given the current state. All right, this is a set valued correspondence or mapping. A lot of times I'll call it the constraint correspondence in these problems. Right, in other words, if you think about the planner trying to choose the control yt at date t, she can't just pick any value she wants. She's constrained by the underlying resources in the problem, right? G tilde basically shows kind of the menu of feasible options that the planner can choose from when selecting yt. It's the feasibility set, right? Or the constraint correspondence. What is f tilde? Well, f tilde, unlike g tilde, is actually a function. It maps elements of x product y into the space x. This specifies the evolution of the state. Sometimes it's called the state transition equation in these types of planning problems. In other words, what it does is it takes the value of the state at date t, xt, and given what the planner chooses for the control yt, those two things together are going to determine what the state of the world is going to look like at the beginning of date t plus 1. Okay, that's xt plus 1. So it determines what next period's state vector is going to look like as a function of today's control. F tilde is a function, G tilde is a constraint correspondence. All right, any questions so far? Now look, I say all of this, but it's oftentimes going to be useful to transform these types of dynamic programming problems into one that actually eliminates YT from the model, okay? This is what we're going to do to the optimal growth model. We're going to kind of reduce the dimensionality of the problem here. Let me do the following transformation. I'm going to define this function V star of x0 as the following. It's going to be the maximized value of the x sequences of the sum from 0 to infinity of beta to the t u of xt comma xt plus 1, subject to xt plus 1 is some element of g of xt with x not given. Okay? In other words, what I've done, imagine doing the following thing here. Go back up to this canonical model and use this state transition equation, f tilde, to solve for yt in terms of xt plus 1. Imagine taking the inverse function of f tilde, for example, okay? And then simply plugging that value into the utility function or the payoff function. What you're going to get is some new transformed payoff function that's a function of xt and xt plus 1, and the control yt has been taken out of the model or taken out of the problem. Okay, here I'm gonna let xt, of course, be an element of the space big X, which I'm just gonna say is a subset of Rk. So I'm gonna get rid of the kx index and just say k is some integer. Xt is the state, and what becomes the control in this problem? Well, the value of tomorrow's state effectively becomes the control. U then maps elements of x times x into the reals, and the constraint correspondence G, maps elements of x into x. So G shows all the feasible values of xt plus 1 given what xt is. Now, one other piece of notation that has been developed here is this function V star. This is a function that maps elements of x into the reals, and it is indeed a function. This has a very important place in the study of dynamic programming. It's called the value function. The value function specifies the maximum value that the overall objective function can take if the planner has pursued an optimal sequence of x's over time. okay? Another way to think about V is a infinite horizon indirect utility function. You guys studied indirect utility in micro yet? Or like a cost function maybe? Have you done any of that yet in micro?
The expenditure function.
Yeah, expenditure function. Okay, yeah, that's so these are functions that are once you minimize expenditures or you maximize profits, you can derive a profit function or an expenditure function where you substitute in the maximized values of those choice variables. In which case, the expenditure function shows you how the minimum value of expenditures given the prices of the various inputs, right? And you can see how changing the prices is then going to affect expenditures. But it implicitly assumes optimal behavior, right? That's what this is. It's kind of like an indirect utility function, right? Except it's a lifetime utility function. Now, just to provide a little context here, imagine the optimal growth model, right? Which is a planner choosing sequences of consumption and capital over time to maximize some guy's lifetime utility function. Well, what's the natural control there? It's consumption, right? And what's the state? It's the capital stock at the beginning of the period. Well, you can take the constraints in the model and substitute consumption out of the problem, in which case the control is now going to be KT plus 1, right? Think about it. Your consumption decision today determines your investment or savings decision, right? One is just the residual of the other. And that investment savings decision, of course, determines how much capital you have at the beginning of the next period. So KT plus 1 can be taken as the control variable, the relevant control variable in those type models, where KT is the state variable in period T. So it's quite easy to transform this type of problem into one that looks like this. It's the same thing, except you're treating XT plus 1 as the relevant control variable. Okay, when the maximized value of the overall objective function is attained by some sequence, let's call it X star, all right. Let's say this sequence of X stars is the one that maximizes the overall objective. In other words, it's the argument or the arg max of the sum from 0 to infinity of beta to the T U xt xt plus 1 subject to xt plus 1 is an element of g of xt, x not given. This sequence of optimal x's I'm sometimes going to refer to as the solution or the optimal plan to the planner's objective function, okay? So make sure you understand the terminology there. The sequence of x's that maximize or achieve the maximum value of the overall objective function is what we refer to as the solution or the optimal plan to this planning problem, okay? Now, of particular interest in dynamic programming problems is, of course, the value function, V star of xt. V star is interpreted as the value of pursuing this optimal sequence of x's, these x stars over time. The whole point of dynamic programming, I guess, is to try to characterize the optimal solution or optimal plan, x star, as well as the value function. We want to be able to do both of those things. So not only solve for the optimal sequence of controls, but we also want to be able to analyze or characterize the value function. Okay, let's do an example, because I want this stuff to be as clear and as intuitive as possible. Let's just state the basic optimal growth model. We won't study it until next week, but I want to show you how it maps into this canonical form we've been discussing, okay? Okay, so what is the basic setup of the optimal growth model? Unlike the overlapping generations model, where agents are choosing their lifetime consumption subject to income constraints every period of their life, here you have what's called a representative agent, or a homogeneous agent, that has the following lifetime utility function. So he lives forever, okay? And he discounts his utility by beta, and his utility depends on his own consumption, okay? And what the benevolent social planner wants to do in the optimal growth model is to choose sequences of capital stocks and consumption that maximize the representative agent's utility over this infinite horizon, subject to not income constraints, because this isn't a decentralized problem, but rather subject to a resource constraint, right? Remember, the planner can choose allocations and just drop them wherever, okay? So the planner is not constrained by income constraints, but rather by the aggregate resource constraint in the economy, which in this case is going to be what? Consumption plus investment. What's investment or savings? Is KT plus 1 minus 1 minus delta KT. That has to be equal to total output in the economy, right? So whatever is produced in period T has to be used for either consumption or savings, that is investment. You can either augment the capital stock with investment, or you can eat consumption. The planner is also constrained by the fact that the capital stock has to be non-negative. And she's also constrained by the fact that capital is given in the initial period. This utility function is assumed to be continuous and map elements of the positive reals into the reals. So consumption is also non-negative. This is the statement of the basic optimal growth problem, which we will analyze in much greater detail next week, right? That is, we will examine whether this model admits a unique steady state and whether it's stable, and look at some properties of that steady state. But for right now, I want to show you guys that it's very easy to transform this, or to represent this problem as a kind of a canonical dynamic programming problem, okay? What's the control here for the planner? Consumption, right? What is the state? What does the planner take as given at the beginning of date T? Capital. That's what is carried over from the previous period, right? The planner's choice of consumption, given what the state is, then determines what's next period's capital stock is going to be. So we can transform this problem by taking consumption out of the model and simply maximizing over choice of KT the sum from 0 to infinity, beta to the t, u of CT. Well, what is CT? That is f of KT plus 1 minus delta KT minus KT plus 1, subject to KT is greater than or equal to 0, with K not given. So you see here how the utility function, or the instantaneous payoff function, depends not just on KT, it also depends on KT plus 1, right? KT is the state, KT plus 1 becomes the new control. Now, one thing that I want to clarify here is this constraint correspondence. What is G equal to here? Remember, KT plus 1, that is the planner's choice of next period's capital stock, is constrained to some extent. It has to live inside of this set valued mapping G. Well, what does that mapping look like? We should be able to determine exactly what it is given the constraints on the model. Well, what do we know that capital can't ever go below? Capital is constrained to be non-negative, right? So we know that KT plus 1 is bounded from below by 0. Is there some natural upper bound that KT plus 1 has, given the value of KT? Remember, we're looking for basically the menu of options that the planner has here to choose KT plus 1 from. What's the highest possible value that KT plus 1 can be? Well, what if the planner chose 0 consumption? Go back to this state transition equation. If the planner selected 0 consumption, then what would KT plus 1 be? F of KT plus 1 minus delta KT. This interval here, closed and bounded interval, shows all of the possible values that the planner can select for KT plus 1. Can't be less than 0, and it can't be bigger than F of KT plus 1 minus delta KT. You see how G here is a function of the current state. This is the set valued mapping, which tells us all the feasible options that the planner can choose for KT plus 1. This is what's called the constraint correspondence, and corresponds to that G in the generic problem we just got done talking about.
So what is, that's not savings though. What is that? What would that be called?
What is what called?
The upper bound, the F K plus.
It's just, G is just, think of it as the menu of possible values for KT plus 1 that the planner can select. Her objective is to try to maximize this thing. It in general will not be optimal to select the highest possible value of KT plus 1. Why? Because you're going to be minimizing consumption in that case. But this shows what the bounds on KT plus 1 are. They're constrained in some sense. This is not an unconstrained problem. It's a constrained one. Now, if we let K star correspond to an optimal solution or optimal plan to this problem, then it follows that the value function, given some initial capital stock, is just equal to the infinite sum of the discounted values of the period payoffs. F of K star plus 1 minus delta K star minus K star T plus 1. When we study the optimal growth model, we're going to characterize the optimal plan as well as the value function, which is the value of pursuing an optimal plan for all t. Does that make sense? This puts some flesh on this canonical dynamic programming problem so you can kind of see what the various pieces are. You need to know what a state vector is. You need to know what the control is. You need to understand the instantaneous period payoff function. You need to know the difference between the state transition equation, F, and the constraint correspondence, G. That constraint correspondence is really important. That's going to be a key component of these dynamic programming problems. There should be enough given in the problem in order to figure out what the feasible set of values for the control are. The control is going to be constrained by something inherent in the problem. All right, let's go back to talking about just generic stationary dynamic programming. Okay, I want to consider first what I call just the sequence problem. It's stated as the following. V star of x0 is the maximized value over sequences x that maximize the discounted sum of instantaneous payoffs, u of xt, xt plus 1. Subject to the constraint correspondence, xt plus 1 is an element of g of xt with x0 given. You need to get very, very comfortable with writing down these dynamic problems and understanding the different pieces. There's a value function, there's the overall or lifetime objective, and then there's the constraint correspondence. They're all important pieces of the problem. Okay. SP corresponds to sequence problem. That is a version of this infinite horizon optimization problem that I want to talk about here for a minute. The sequence problem, SP, involves choosing an infinite sequence of these x's, a countable infinite sequence of x's. Now, in practice, the solution to these sequence problems, that is characterizing this infinite sequence of x's, is often difficult to do both analytically or even numerically, okay? So in other words, the basic dynamic programming, or I should say infinite horizon optimization problem presented as a sequence problem, it is difficult to do, okay? The whole point of what we call dynamic programming is to transform this sequence problem into a different problem, okay, that is easier to deal with. That problem is what's known as a functional equation, okay? Now let me write down what the relevant functional equation is that corresponds to this sequence problem. Looks like the following. V of x, which is again a value function, but this V here doesn't necessarily correspond to V star. V instead is the value of pursuing an optimal plan that satisfies this functional equation. The functional equation looks like the following. Max of, let's call it x prime, as an element of some set G of u of x, x prime, plus the discounted value of V evaluated at x prime. For all x in big X, where V maps elements of x into the reals. This is what's known as a functional equation. In a few minutes, we'll talk about it being called what's called a Bellman equation, okay? Again, V here refers to the function determined by the maximum value of the right-hand side of the functional equation. V star is the value of pursuing an optimal plan to the sequence problem. Okay, now the difference between the sequence problem and the functional equation is pretty straightforward. In the sequence problem, you have to characterize a countably infinite number of x's over time. That's what you're looking for, is this sequence of x stars. In the functional equation, you're actually looking for something different. Instead of an infinite number of x's, what you're looking for is a single, what's called policy function. Which I denote x prime. What x prime determines is essentially the optimal value of the control, that is xt plus 1, as a time invariant function of whatever the state is at date t, that is xt. So what x prime determines then is a policy function which shows you how xt optimally maps into xt plus 1, right? So the sequence problem involves solving for an infinite number of objects. The functional equation, however, involves only solving for one object, and that is a policy function rather than an infinite number of controls. Okay, now you might be confused by the absence of time subscripts here in the functional equation. In most cases, the utility function does not depend on time directly, right? It only depends on time indirectly because of the values of the x's. This suggests that the optimal way in which xt maps into xt plus 1 should not actually depend on the time period. In other words, the way that x2 optimally depends on x1 is exactly the same way that x100 depends on x99, right? That's what x prime is it's the mapping from xt to xt plus 1 that solves this maximization problem. Okay, so mathematically then, finding this policy function is the same as just maximizing the right-hand side of this equation. That is u of xx prime plus the discounted value of tomorrow's value function. There is one complication that's rather obvious though, right? That makes this different from the standard type of maximization problem you would see in your calculus class, that is. And that's the appearance on the right-hand side of the value function, right? In other words, if you were to maximize this thing on the right-hand side, it would tell you what the value function is, right? Unfortunately, that value function argument is an argument inside the maximum. It makes this problem recursive. That's the language that is used to describe these types of problems. It is a recursive maximization problem. That the optimal value of V in some sense depends on knowing what V is already. Okay, so when I talk about transforming the sequence problem into recursive form, I mean writing the equivalent value function, which is also called the Bellman equation, named after mathematician Richard Bellman, who first analyzed these types of problems. Okay. All right. Hopefully this will clear up some more of the confusion. The form of this functional equation follows naturally from the sequence problem. Okay. Let's start with the sequence problem for a second. All right. Let's write out what V star of x0 should look like. It's the sum from 0 to infinity, beta to the t, u of xt star, xt plus 1 star. Right? If we substitute in all the optimal values for the x's, we get V star, right? Well, we can actually write that as we can break up that infinite sum, right? That's u of what? x0, x1 star, plus beta u of x1 star x2 star plus beta squared u of x2 star x3 star plus dot, 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 right? Well, imagine splitting this infinite sum into two components, u of x0, x1 star, plus, now factor out a beta from the rest of the sum, and you get a beta times the sum from j is equal to 0 to infinity of beta to the j times u of xj plus 1 star, xj plus 2 star. Now, what does this infinite sum look like to you? Well, to me, that just looks like the value function starting at x1 instead of x0, right? So v star of x0 is just u of x0, x1 star, plus beta v star of x1 star. So what have we done? We've taken this maximized sequence problem and we've split it into two components. The optimal value of the current return plus the discounted value of the optimal continuation return. This equation here encapsulates the basic idea of dynamic programming, which is called the principle of optimality. I'm going to state it more formally here in a minute, but basically it says that the solution to a sequence problem can be broken into two parts: what is optimal today plus the discounted value of continuing with that optimal plan from date one onwards. Okay, dynamic programming basically exploits this principle. And you see here that this, hopefully you guys can see this, looks just like the Bellman equation, right? That's how the two are related. Okay, let me step back for just a second because I'm getting some glassy-eyed looks here. The central planner that is trying to maximize the lifetime objective function here is faced with this problem. It's faced with a sequence problem. What I'm telling you is that problem is difficult to analyze. It's annoying to work with because you have to find an infinite number of x's. It's much easier to transform this problem into its recursive form and simply find a single policy function that shows how the state maps optimally into the control. However, solving that transformed problem is only valid if what? If we can be sure that solutions to the transformed problem correspond to the same solutions of the sequence problem. What's the point of transforming a problem into something that's easier to work with if the solutions to the two problems don't coincide, right? There's no point to doing that. So that's the only way in which this is valid. So basically the whole point of our discussion today and really into the next class is going through the various assumptions that are needed to establish the theorems which guarantee the equivalency between these two problems. The sequence problem is what the planner is going to be faced with. That's the kind of problem I'm going to give you on an exam. Your task will be to transform that problem into its relevant Bellman equation and solve for the policy function. Doing it that way is only valid if the solutions to the Bellman equation correspond to the solutions to the sequence problem, right? And that's the challenge at hand, is establishing under what conditions SP and FE give you the same solutions. Now, like I said, the notable advantage of solving the functional equation instead of the sequence problem version of this exercise is that the solution can be represented as a time invariant policy function, okay? That policy function, I'm going to denote pi. It takes elements of x and maps them into x, okay? In other words, the optimal value, let's say of xt plus 1, can be written as some time invariant policy function pi of xt. The sequence problem involves finding this object. There's a countable infinite number of those x stars. The Bellman equation or functional equation version of this problem involves finding one object, and that's pi, the policy function. How does the planner optimally choose xt plus 1 given what she knows about the state xt? Now, once you have identified the value function, that is v, the policy function is fairly straightforward to characterize, right? What is v of x going to be equal to? Well, that's just u of x. What's the maximized value of x prime? That's just pi of x plus beta times v of x prime. Well, x prime, again, is just pi of x. So once you've obtained the policy function, you've obtained the value function, or vice versa. Once you've obtained the value function, you have an equation that determines the policy function, pi. The point of dynamic programming is to characterize pi and v. And I'm telling you that it's a lot of times easier to work with this problem than it is the sequence problem. Okay, any questions so far? I don't have a tremendous amount of time left. I may only be able to get through. So here's how the rest of the discussion is going to go. There are about 5 or 6 dynamic programming theorems that I want to present and talk about. My intention is not to prove any of them. Okay, the proofs of these theorems require more complicated real analysis and some functional analysis. Okay, the proofs are actually in your textbook if you want to see them. I think that's a little bit beyond the scope of this class. Really, what I'd rather you gain from this is a kind of a workman's understanding of how to use these theorems and apply them to dynamic macro problems. All right. So the way I'm going to approach this is there are a set of assumptions that must hold in order for the theorems to be established. There's about 5 or 6 theorems that I want to go over. So what you're going to find in your notes is a list of those assumptions and some discussion about them and a list of those theorems. I'm going to kind of go back and forth. In other words, I'm just going to state the assumptions that are needed to establish each of the theorems one by one. Okay, so I'm going to kind of bounce back and forth here between assumptions and theorems over the rest of this class and through the next class. Okay, and hopefully once we're done, you guys will have more of a kind of intuitive understanding about what the Bellman equation is and how to set up a Bellman equation and characterize the solution to one. Okay, so this section is what's called some useful theorems. Now, before we start going through these assumptions and theorems, let me set up a little bit of notation that's going to hopefully ease the discussion somewhat here. So we've already talked about X star as corresponding to the solution to the sequence problem, right? And V star is the value of pursuing that optimal strategy over time. Let me define this term phi of xt as the following. This is going to correspond to a set, and the elements of this set are themselves sequences. xs from s is equal to t to infinity, such that xs plus 1 is an element of g of xs, right? For s equal to t, t plus 1, etc. In other words, what phi of xt is the set of all feasible sequences of x's starting from date t onto infinity. So in date t, when the planner is trying to decide the sequence of x's over time, there's some set of all possible feasible sequences, right? Not every sequence of x is actually feasible because it might violate the constraint correspondence. So the menu of all feasible options, we're going to group together in this set and call it phi of xt, okay? So for example, a typical element, let's say x bar of phi of x0 is going to be a countably infinite large element that looks like the following, you know, x0, which is given, x1, x2, blah, 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 where each of these x's is feasible. That is, it lives inside of the constraint correspondence defined by the previous value of x. All right, what is the very first assumption that we need to have be satisfied in order for our dynamic programming theorems to be applicable here? Assumption one, and look, a lot of this, it's directly in your notes, so I'm gonna just write down minimally what I need, okay? And you guys are just welcome to read it off on your own, but assumption one says that the constraint set G is non-empty for all x and big X. And for any initial value of x, and for all feasible sequences of x, the limit as n goes to infinity of the sum from 0 to n, beta to the t, u, xt, xt plus 1, exists and is finite. That is the thrust of assumption one. Okay, now what does it mean? Let's translate this. The first part of assumption one, that gx is non-empty, it means that G is not the null set. In other words, there's something in G for the planner to choose from. When you go to the restaurant and you open up the menu, there's actually items on the menu to choose from. If you open up the menu and it's just a blank piece of paper, it's the empty set, right? So here, this assumption basically just says that the planner actually has some menu of options to choose from. It's non-empty. It ensures that the maximization problem has kind of well-defined choices.
So that means the set has to have at least two choices instead of just one?
It just has to have one choice. It has to be non-empty.
Okay.
Yeah. What does the second piece of this assumption say? The overall objective function that the planner is trying to maximize has to exist and be finite. Well, that's not really controversial, right? And particularly in economic applications, we're interested in optimization problems that are finite, right? Agents don't have like infinite resources. Anytime you do a maximization problem in a mathematics class, that the thing that you're maximizing over has to exist in the first place in order for it to be a well-defined problem. So all we're saying here in assumption one is that the constraint set is non-empty and that the overall objective function that the planner is trying to maximize exists and is some finite object. for any, now let me be careful about this. This is for all initial x and for all x bar in phi of x bar. That is, for any feasible sequence of x, this thing has to exist and be finite. Not just the optimal sequence, but any feasible sequence that the planner could choose. This thing here has to be finite. Okay, questions about that? Assumption 1 is the only one of our list of assumptions that is needed to establish Theorem 1 in dynamic programming. And that's what your textbook author characterizes as equivalence of values. Okay. Suppose that assumption 1 holds. So G is non-empty. The lifetime objective function exists. Then for any little x on big X, any maximized value of the value function V star to the sequence problem also obtains the maximum value of the functional equation. Moreover, any maximum value of the value function in the functional equation or the Bellman equation, V of x, is also obtains the maximum value of the sequence problem, so that V star of x is equal to V of x for all x in big X. So this theorem basically says that if assumption 1 holds, both the sequence problem and the recursive Bellman equation formulation of that problem achieve the same value. Let me say that again. If you have found some sequence of x's that obtain the maximum value of the sequence problem, that is, you've characterized V star of the sequence problem, whatever that value is also the maximum value of the functional equation, that is V of x. Or in reverse, if you have found the V that obtains the maximum value of the Bellman equation, you have also found the V star that maximizes the sequence problem. So V star is equal to V for any possible value of x. The next theorem is going to establish an even more important result, that solutions to the sequence problem, that is the optimal plans, the x stars, also coincide with the solutions to the functional equation or the Bellman equation. So what Theorem 1 does is it establishes the equivalence of the value function. Theorem 2 establishes more or less the equivalence of the solutions or the optimal plans to each of those two problems. Theorem 2 also only requires that assumption 1 hold. You don't need anything else. Theorem 2 is what your textbook author calls Principle of Optimality. Okay, let us suppose again that assumption 1 holds. And let's assume that x bar star, which is an element of phi of x0, it's one of these feasible plans, attains the maximum of the sequence problem. That is, it obtains V star of x0. If that is the case, then V star of x0, let's say of xt star, let me do this starting from some date t, can be broken into two components, all right? This is the most important theorem for dynamic programming. That the maximum value of this sequence problem, V star, can be written as U of X star T plus 1, plus beta V star of X T plus 1 star. Moreover, if X bar star satisfies the functional equation, in other words, it attains the maximum value of V, then X bar star also satisfies the sequence problem. Now let me stop here and carefully explain what this is saying. This theorem states that the value of pursuing an optimal plan, let's call it, that optimal plan is X bar star, of the sequence problem can be broken into two components. All right, so let's say you found this X bar star that maximizes the sequence problem and obtains V star, the value function of the sequence problem. That value function can be broken up into two components because of this principle of optimality. The optimal value of the current return, U of X star T plus 1, plus the discounted optimal continuation return, that is V star X star T plus 1. Now, in view of the fact that V star, remember, V star is equal to V by Theorem 1, by the equivalence of values, right? We just showed that in Theorem 1. Then this principle of optimality here, which says we can take the V star and break it into these two components, implies that V of X T star is equal to U of X T star, X T plus 1 star, plus beta V of X T plus 1 star. Now pay attention to the notation there. This is the Bellman equation, right? The principle of optimality says that we can break the sequence problem into this. We can take an infinite horizon sum and break it into a two-period problem. The current return plus the maximized discounted return. Now, Theorem 1 says that V star is equal to V. So that implies then that we can simply write that equation not as V star is equal to U plus beta V star, but as V is equal to U plus beta V star. Therefore, if we have found a solution X star to the sequence problem, we've also found a solution to the functional equation. That is the Bellman equation. That works in reverse as well. If we have found an X star that satisfies this Bellman equation, then because of the equivalence of values, it also satisfies this equation, which due to the principle of optimality is the maximized value of the sequence problem. Why is that so important? Because if assumption 1 holds, then there is no risk of excluding potential solutions to the sequence problem by solving the functional equation instead. That's together what theorems 1 and 2 are saying. That if you're faced with a sequence problem that is difficult to solve, you can transform it into a Bellman equation, and the solutions you get out of that Bellman equation will necessarily be the same solutions that you get from the sequence problem. You're not going to risk excluding any possible solutions to the sequence problem by solving the Bellman equation instead. We've basically established here through these two theorems the equivalence of the two problems.
Oh, and it kind of like link back to what you were saying earlier about when you minimize your cost and those units that minimize your cost, actually those that, you know, maximize your profit.
You can think of it as a form of duality, yes.
Oh, yeah.
Yeah, if you want to think about it like that, you can. If that helps you, that's fine. That's not usually the way I think about it, but the way I like to think about it is that you've got this sequence problem, and you can see that if you found an optimal sequence of x's, these so-called x stars, if you plug them into the infinite horizon problem, you can break that infinite sum into two pieces: the current return or the current payoff plus the discounted sum of the rest of the payoffs. Well, that's nothing more than the value function starting from period 1 instead of period 0, right? And so that suggests then that the Bellman equation, which takes that form, is going to give you solutions that the sequence problem would give you. That's essentially what the principle of optimality says. And it turns out that in a lot of these problems, first of all, what we're really interested in is the policy function. That is how the state maps in to the control, right? What did we look for in the Solo model or the OLG model? Was the savings locus, how KT maps into KT plus 1. That's what we're going to look for in the growth model. Well, that's a time invariant policy function, how KT plus 1 is determined optimally given the value of KT. Dynamic programming is going to help us characterize that particular map. It's going to help us solve for that particular mapping. We need these tools to find them in an infinite horizon problem. It's not, you can't do it as easily as you did in the OLG model or even in the Solo model, which is really easy to do. It just takes a few substitutions. Okay, so I think it's interesting here that this equivalence result that we've established now that we can work with the Bellman equation instead of the sequence problem directly and still get the same solution, only requires one assumption. What are the two pieces of that assumption? That the constraint set is non-empty, that there are some well-defined choices that the planner has, and that the lifetime objective function, this infinite horizon utility objective, exists and is finite. As long as you're willing to make those two assumptions, you get equivalency between the Bellman equation and this sequence problem. Let me tell you what we're going to do on Wednesday. My plan is to finish all of these theorems. The next theorem that we're going to look at establishes what does it establish? I've lost my page. Theorem 3 establishes the existence and uniqueness of the Bellman equation. So there are a couple of assumptions we need to make about the state space in this model that we haven't said anything about. Capital X in particular, that is the set of values that the state vector is drawn from. If we make some assumptions about the behavior of that space, then we can conclude that the Bellman equation itself is unique and exists, and therefore solutions to the problem exist. Now, how do we guarantee the existence of a unique solution to the problem? That is a unique policy function that shows how xt is mapped into xt plus 1. You need the value function to be strictly concave. In calculus, how do you guarantee the existence of a unique extremum point? Well, you have strict concavity of the objective function. Well, we need to demonstrate how we can guarantee concavity of the value function. That, as you might guess, requires assumptions about the concavity of the utility function. Okay. The last few theorems that we're going to talk about are really more about properties of the value function that are going to be useful for us. Mainly the monotonicity of the value function, meaning that if you increase x, you also increase the value function. Okay? In the same way that if you increase prices, you increase the profit function, right? Or if you increase wages, you increase the cost function. That's going to be useful when we're trying to prove properties of the equilibrium in the optimal growth model, in particular, the existence and uniqueness of a steady state and its stability. Another property of the value function we want to establish is its differentiability, which draws directly from the differentiability of the value function. And that'll be it. The last part of the discussion is, so there's one more piece to this puzzle that we've got to talk about. I know I'm running out of time, but it turns out that when you want to characterize the solution to these infinite horizon optimization problems, you can't just derive what would be equivalent to like first order conditions from a Bellman equation, which I'll show you guys how to do that. Okay, when we establish the existence and uniqueness of the Bellman equation, you can then write it down and write the first order conditions that correspond to it. Okay, but there's one more condition that's going to be necessary to fully characterize the solution to these infinite horizon optimization problems. And it's what's sometimes characterized as a boundary condition at infinity, more formally known as the transversality condition. This is a very important optimality condition to this class of models that we didn't talk about in the OLG model. There's not an equivalent concept in that model. It turns out that that transversality condition is going to have big implications on the optimal growth model and the neoclassical growth model that we talk about in the coming weeks. So that's kind of the last thing we'll do. We'll probably be able to start talking about that on Wednesday, but I might not fully finish that discussion until the following Monday. Okay? Study for your exam, but you know, be looking over this stuff so that it's not completely foreign to you. All right? The goal here is not, again, is to be able to understand these concepts. What is a value function? What is a policy function intuitively? How do you take a sequence problem and transform it into its equivalent Bellman equation? Those are the kinds of things that you're going to have to be able to do in this class. And then once you do that, we can figure out how to optimize the Bellman equation and get all of the first order necessary conditions and the transversality conditions. Okay? All right.